My name is Jamie Elgeo G. Rolona, and we're going to talk about domestic wastewater treatment. Wastewater has historically been considered a nuisance to be discarded in the cheapest, least offensive manner possible. This meant the use of on-site disposal systems such as the pit privy and direct discharge into our lakes and streams. Clean water is a scarce commodity. It should be treated as such and conserved and reused. Wastewater treatment categorization. Secondary treatment. The major purpose of secondary treatment is to remove the soluble BOD that escapes primary treatment and to provide further removal of suspended solids. A variety of approaches have been used in the past to meet these basic needs. The most common approaches are activated sludge, trickling filters, and oxidation pans or lagoons. Advanced or tertiary wastewater treatment. These processes include chemical precipitation, granular filtration, membrane filtration, and carbon absorption. As conventional processes, they are better termed tertiary treatment processes rather than an advanced treatment process. In current practice, the employment of air stripping, ion exchange, NF or RO treatment, and the other similar process to meet water quality requirements is correctly termed advanced wastewater treatment. Overview of wastewater treatment systems. Primary treatment. Screening. Barracks. Typically, the first device encountered by the wastewater entering the plant is a barrack, shown in Figure 8.2. The primary purpose of the rack is to remove large objects that would damage or foul pumps, valves, and other mechanical equipment. This is a sample picture of a bar rack. Bar racks or bar screens may be categorized as trash racks, manually cleaned racks, and mechanically cleaned racks. Trash racks are those with large openings, 40 to 150 mm, that are designed to prevent very large objects such as logs from entering the plant. These are normally followed by racks with smaller openings. Next is the grit chambers. Inert dense materials such as sand, broken glass, silt, and pebbles is called grit. If these materials are not removed from the wastewater, they abrade pumps and other mechanical devices, causing undue wear. There are two basic types of grit removal devices, the aerated and vertex. Aerated grit chambers. The spiral roll of aerated grit chamber liquid drives the grit into a hopper which is located under the air diffuser assembly, as shown in Figure 8.3. Aerated grit chamber performance is a function of the roll velocity and detention time. The roll velocity is controlled by adjusting the air feed rate. Grit accumulation in the chamber varies greatly, depending on whether the sewer system is a combined type or a separate type, and on the efficiency of the chamber. Normally, the grit is buried in a sanitary landfill. This is a sample picture of aerated grit chamber. Vortex grit chambers. Wastewater is brought into the chamber tangentially, as shown in Figure 8.4. At the center of the chamber, a rotating turbine with adjustable pitch blades along with a cone-shaped floor produces a spiraling donut-shaped flow pattern. This pattern tends to lift the lighter organic particles and settle the grit into a grit sump. This is a vortex grit chamber. The effluent outlet has twice the width of the influent flume. Secondary treatment. Secondary wastewater treatment implies that the major mechanism used for treating the wastewater is biological process, activated sludge, aerator systems, and trickling filters. Activated sludge. The activated sludge process is a biological wastewater treatment technique in which a mixture of wastewater and biological sludge microorganisms is agitated and aerated. The activated sludge process derives its name from the biological mass formed when air is continuously injected into the wastewater. In practice, wastewater flows continuously into an aeration tank where air is injected to mix the activated sludge with the wastewater and to supply the oxygen needed for the organisms to break down the organic compounds. Activated sludge design and operational parameters. Mean cell residence time (MCRT). The main design and operational parameter for the activated sludge process is the mean cell residence time. A qualitative definition of MCRT is the total biomass in the system divided by the biomass wasted from the system. This is the formula for the mean cell residence time. Hydraulic detention time, the time that the wastewater resides in a particular unit operation or process, is called the hydraulic detention time. This is the formula for the hydraulic detention time. Food to microorganism ratio. Another design and operational parameter is the food to microorganism ratio, which is defined as follows. This is the formula for food to microorganism ratio. Biochemical kinetics of complete mixed activated sludge systems. Here is the relationship between net growth rate and MCRT. Effluent soluble substrate equations. Substrate removal in activated sludge systems has been modeled using various expressions. Substrate utilization using a Michaels-Menten type equation was proposed by Lawrence and McCarthy in 1970 and is one of the most widely accepted equations. With a working formula of with a final formula form of minimum mean cell residence time. Biological wastewater treatment systems should not be operated at the minimum mean cell residence time. Total effluent substrate concentration. Regulatory agencies and NPDES permits generally list effluent BOD5 requirements in terms of the total BOD5. The formula of this is TBOD5 equals PBOD5 plus SBOD5, where TBOD5 is total 5-day biochemical oxygen demand milligram per liter. PBOD5 equals particulate 5-day biochemical oxygen demand milligram per liter. SBOD5 is soluble 5-day biochemical oxygen demand milligram per liter. The formula in getting PBOD5 is this. Oxygen requirements. The heterogeneous culture of microorganisms in the aeration basin primarily consists of aerobes. Therefore, they require oxygen to meet metabolic requirements. Oxygen serves as the electron acceptor in aerobic processes, with the ultimate end product being water. The total quantity of oxygen required to meet process requirements is calculated using equation 7.104. If nitrification is not desired, a MCRT less than 5 days is typically used, and the NOD term in the equation is set equal to 0. And this is the equation. Aerator systems. It has two types. First is the mechanical aerator. Mechanical aerator consists of mixers or brush rotors that transfer oxygen into wastewater by spraying the wastewater into the air. Second is diffuser or diffused aerator system, are similar to fish aquarium tanks with oxygen is diffused through a diffuser stone or membrane, thereby transfer oxygen into wastewater. These pictures shows the difference between the two aerator systems. Trickling filters, an alternative biological process that was often used before activated sludge systems had gained wide acceptance, is the aerobic attached growth process called the trickling filters. Trickling filters are not primarily a filtering or straining process as the name implies. Trickling filters do not filter the wastewater like a traditional sand filter. Instead, the biomass growing on the media uses the organic matter, along with a portion of the nitrogen and phosphorus to grow new microorganisms. This is a sample picture of a trickling filters. Second, clarification. Proper separation of biological solids from the wastewater must be accomplished during secondary clarification to ensure successful operation of activated sludge or any biological process. If biological processes are to operate properly, it is essential that secondary clarifiers must be designed correctly, as shown in this picture. Second, clarifier design. The surface area of the secondary clarifier, based on the clarification, is determined by dividing the design flow rate by the overflow rate according to the following equation. And this is the formula for the secondary clarifier's surface area based on thickening considerations. In this formula, instead of using limiting solids flux value, we use the SLR, or the solids loading rate. Disinfection of wastewater. The last treatment step in a secondary plant is the addition of a disinfectant to the treated wastewater. The addition of chlorine gas or some other form of chlorine is the process most commonly used for wastewater disinfection in the United States. Primary disinfectants include chlorine, chlorine dioxide, chloramines, ozone, and ultraviolet radiation. Chlorine is injected into the wastewater by automated feeding systems. Wastewater then flows into a basin where it is held for about 15 minutes to allow the chlorine to react with the pathogens. Chlorination of wastewater. Chlorine is delivered to wastewater treatment facilities as a liquefied gas at high pressure in containers ranging in size from 150 pounds or 68 kilogram cylinders through 1 ton or 908 kilogram cylinders all the way up to railroad tank cars, which may contain up to 55 tons or 49.9 milligrams of chlorine. Chlorine may be applied either as a gas or in aqueous solution. Chlorine contact basins generally consist of long rectangular serpentine channels to allow chlorine sufficient time to react with the pathogens in the wastewater. Sludge treatment and disposal. Sludge mass volume relationship are important when designing solids handling and treatment systems. The specific gravity of sludge is calculated using the following equation. This is the formula for the volume occupied by the sludge. Sludge thickening, separating as much water as possible by gravity or flotation. Thickening is usually accomplished in one of two ways. The solids are floated to the top of the liquid or are allowed to settle to the bottom. Sludge stabilization. The principal purposes of sludge stabilization are to break down the organic solids biochemically so that they are more stable and more dewaterable and to reduce the mass of sludge. If the sludge is to be dewatered and burned, stabilization is not used. There are two basic stabilization processes in use. One is carried out in closed tanks devoid of oxygen and is called anaerobic digestion. The other approach injects air into the sludge to accomplish aerobic digestion. The aerobic digestion of biological sludges is nothing more than a continuation of the activated sludge process. Aerobic digestion is accomplished by aerating the organic sludges in an open tank resembling an activated sludge aeration tank. The anaerobic treatment of complex waste involves three distinct stages. In the first stage, hydrolysis, complex waste components, including fats, proteins, and polysaccharides, are hydrolyzed to their component subunits. The second stage, acidogenesis, is commonly referred to as acid fermentation. In the third stage, Methanogenesis is the bacterial conversion of fatty acids and hydrogen into CH4 and CO2 by strict anaerobes. Dewatering. Dewatering is a unit operation primarily accompanied by mechanical means. The objective of dewatering is to increase the solids content of the sludge, thereby reducing the volume of sludge that must be handled. Dewatering operations are required to increase the solids content beyond that accomplished during thickening. Sludge disposal. Ultimate disposal of the residuals or biosolids is accomplished primarily by application to agricultural land or burial in a sanitary landfill. The Part 503 rule establishes requirements for the final use or disposal of biosolids that are applied to land to condition the soil or fertilize crops or other vegetation, or placed on a surface site for final disposal, or fired in a biosolids incinerator. The regulations apply to sewage sludge generated from the treatment of domestic sewage that is land applied, placed on a surface disposal site, or incinerated in an incinerator that accepts only sewage sludge. The regulations do not apply to sludge generated from treatment of industrial process waste at an industrial facility, hazardous sewage sludge with polychlorinated biphenyl concentrations of 50 mg per liter or greater, or drinking water sludge. And that's all. Thank you.